Yes.
Modulus.
Modulus. Yes. So today we're starting Unit 6-2. And this is going to be our final unit of the school year, of the semester. We will do a baby, week-long unit over a topic that appears on the benchmark, but we're not going to test over it. You'll just have a quiz at tops. But this will be your last unit test before the benchmark exam. So today we're starting with complex numbers. We covered complex numbers for a bit, about 2 weeks worth of it last semester. So a lot of this is going to be a review. And we're talking about plotting, how to graph them. And then 2 vocab terms associated with complex numbers. Those are modulus and argument. Pretty much everything today is going to be reviewed to some degree, and some of this will look very familiar. Before we jump in, let's remember what a complex number looks like. Recall, a complex number is of the form a plus bi. And remember that a is the real part. And bi is the imaginary part. So you should remember a complex number is a number that is formed with a real number and then an imaginary number, bi, where I is in place of imaginary. That's what the I stands for. Just a few examples of what imaginary numbers look like. Again, hopefully you remember this from last semester. So we have 3 plus 2i. We have 5 minus I, and we have negative 2 minus 7i. So those are all examples of imaginary numbers. Put any number you like in there for A and B. First of the 3 topics is plotting. Plotting, aka graphing. So when you plot complex numbers, you graph the numbers as a point, just like you would on the XY plane, just like you're used to, been doing it since pre-algebra. But these points instead of X comma Y are A comma B. And I'm actually going to graph the 3 examples above. I'll rewrite them again in a moment. But we only need to go out as far as 7 on all sides since that's our highest number. So that's how big I'll make my axes. So take a moment and draw these going out to 7 on all sides. And then you can label as little or as much as your axis as you like. As long as each notch stands for 1, that's fine. And then I'm going to write out my 3 numbers again. 3 plus 2i, 5 minus I, and negative 2 minus 7i. Give you about 30 more seconds as you're still writing any of that down before we start plotting. One other thing, so you're used to calling this in the plane the x-axis and the y-axis. This that we're doing, it looks exactly the same as the real plane, but this is called the complex plane since we're plotting complex numbers. Not something you'll be tested or quizzed over, but it is good to be aware of the distinction. Since we're in the complex plane, these axes go by different names. We'll start with the x-axis. This is referred to as the real axis. And that's where you plot the A value. And then the other axis is the imaginary axis. And that's, of course, where you plot BI. Otherwise, we treat this just like we would normally plot anything else. So let's start with 3 plus 2i. Again, you plot it as A comma B. So this would be 3 comma 2. And you plot it the way you normally plot points. So write 3 up 2. And I'll put a 1 there since that's point number 1. Then the other 2. We have 5, negative 1. There's a negative 1 in front of that I. And our other point is negative 2, negative 7. And I'll plot both of those. So we have 5, negative 1. And then we have negative 2, negative 7. Yes?
Your point 2, why is it at 3?
Oh, I went to the wrong side of 4. Let me fix that. Thank you, I appreciate that. There we go. 5, negative 1, not 3, negative 1. Anything else on plotting before we move on to modulus? Plotting's pretty straightforward, I hope, but you obviously have to know how to plot to do modulus and argument correctly, so it's a pretty important topic to touch on at first. All right, let's move on to modulus. Modulus, the complex numbers distance from 0. Now those three words, distance from 0, are a signal to a different math concept that you learned a few years ago. It's actually quite familiar. A number, any number's distance from 0 is referred to its absolute value. So whenever we ask for the modulus, we're actually just asking for its absolute value. That's it. Now finding its absolute value is a bit more complicated than any other typical number. I'm only going to do one example of modulus. So the problem will just show up as itself, and that's it. There will be no written directions. Absolute value of -3 plus 2i. So that's all that you're going to see, and then you have to understand what the question is. You'll read this as find the modulus. Or if you prefer absolute value, they are interchangeable terms. Modulus specifically refers to complex numbers. This is a 3-step process. I'll write out the steps as I go. First thing I'll do is graph. Graph the number, so just like I showed you. And this number is -3, too, so we don't need a big plane. And this will be left 3 up 2, so that's the notches I'm going to draw. So there's our point. The overall question is, what is that point's distance from 0? 0 in this case being the origin. So the question is, what is this distance right here? That is the question we are answering. And we label this line R. I assume that connects back to radius, like on the unit circle kind of thing. So I'm assuming that's where the R comes from. So that's step 1, graph it. Step 2, draw the triangle. We've used this concept multiple times since second quarter, so this is nothing new. When you create the triangle, we always connect it to the x-axis, never to the y-axis. Drop it down to the x-axis, we create our right angle here.
Why don't you connect it to the x-axis?
To the what?
Yeah. Why don't you connect it to the y-axis?
Because we always connect it to the x-axis. That's just where it's always drawn from. Connecting it to. That's just the relationship.
Okay.
From here, the goal is to find the length of R, and now that you see a right triangle, find the length of the hypotenuse. So we'll use Pythagorean theorem. And we do know the lengths of the two legs. The vertical is 2 units tall. And then the horizontal is 3 units long, but it's -3. Since we had to go left 3, it's -3. So make sure you're including the negatives where appropriate. Now we have 2 of the 3 sides. We use Pythagorean theorem. To find R.
on the test, do you have to draw all that, or can we just put it as your values and plug them in?
The only issue comes when you make a mistake. There won't be that much partial credit I can give if there's not the work there to give the credit to. So it's just kind of it's a risk to take. So if the answer's right, that's fine. But if you get it wrong, there's no work to back it up, I can't help you out much. So that choice is yours. Pythagorean theorem, we have a squared plus b squared equals c squared. And then r, hope you can clearly see, is the hypotenuse. R is our c value, so we plug in r for the c. So we have r squared on the right side. A and b are the legs. They can go in however you like. I'm going to put in -3 for a and 2 for b. Don't forget the squares. And then from here, I assume we'll switch to the calculator. If you type a negative squared into your calculator, make sure you put parentheses around it. Dropping those parentheses would be a major mistake. 13. R squared equals 13. Last time we had a test or quiz that dealt with Pythagorean theorem, a lot of students forgot to square root. Don't forget to square root. So our r value is the square root of 13.
We don't solve it.
What is it?
We don't actually solve it.
What do you mean don't solve it?
We don't have in 3.6.
No, we just leave it as radical. Now, if you remember, anytime we square root both sides of an equation, the number gets that plus or minus. There's two reasons why I'm not writing that down. Number one, hypotenuse in the plane is always a positive number. Number two, reminder, we're finding the absolute value. That's the question we're answering, and absolute value is always positive. So for those two reasons, it must be positive square root 13. It's not even a question. So I'll write that down if you want to. Keep positive since absolute value is always positive.
What do you mean by 2+?
So I was actually going to fill this in anyway. Whenever we square root both sides, you need that plus or minus. It's a rule when you square root both sides of an equation. When you're solving, plus or minus comes in as a symbol. But there's no question it's positive because we're solving for absolute value. On other types of problems, though, it has mattered that we look at plus or minus. But in this one, it doesn't. It's always going to be positive. So just as like a final putting this together, that is our answer. I'm going to put it back in terms of the problem. Absolute value of -3 plus 2i is equal to the square root of 13. Again, just remembering what we are solving for, what all of this means. We found its absolute value. Questions on modulus, absolute value, before we move on to argument. Okay. Argument you have seen. There's nothing I'm going to teach you right here. It's just in a different context. The argument is the angle of rotation . The angle of rotation is also known as theta. We're graphing theta again. Measured from 0 degrees to the complex number. We'll do 2 of these. The most straightforward way is just to ask you to find theta, but there will be times where we'll just say find the argument, and if you don't know what the argument means, what we're asking you to find, obviously it's going to be very confusing. So I'll ask it both ways. Example 1, I'll say find the argument of 6 minus 4i. Again, this process has multiple steps. I will write them out as I go. First step is graph. And when we graph, label alpha and theta. Just like we did in the past, it's the same thing. And we're going right 6 down 4, so we'll be in the 4th quadrant. And I'll draw my axes accordingly. So there's 6, negative 4, 6 minus 4i. And just like the previous problem, you will draw that line from origin to the point. Now we can label alpha and theta. Reminder, this side of the x-axis is 0 degrees and 360, depending on where you're at, which quadrant. So we start at 0 and we go all the way up to where the angle ends. That's our theta, and theta is what we're looking for. So we'll work until that is solved. Alpha is always drawn from the, in this case, A, but I'm going to be lazy, x-axis to our angle. Step 2 is what you would think to do next. Draw the triangle. So again, we connect it up to the x-axis. Create that right angle. And again, we already know these side lengths, so I'll go ahead and fill that in. The horizontal has a length of 6, positive 6, we're on the right side of the x-axis. And then this was down 4, so negative 4 on the vertical. And we don't know the hypotenuse yet. Next, I'll label the HOA, the 3 sides of the triangle. Judging by the last time that this was tested over, some of you guys still struggle a bit, which if you still struggle with this, you need to get that figured out. I don't think this is very difficult. Hypotenuse is always in the same place. It's across from the 90. The opposite O, it is opposite alpha, and it's always on the horizontal, or sorry, the vertical, leaving A to be on the horizontal. A is the side that touches alpha, little a. A and A, they're together. Yes.
Do you need to solve for the hypotenuse?
No, we do not.
Just put an inverse tangent.
Oh yeah, you're already following. Yep, that's exactly what I'm going to do. Okay, so the next goal is to find alpha. Now how we're going to find alpha, we need to use trig. And our 3 trig options, which Devin already gave away where I'm going to go, but I'm going to show you. We have sine of alpha is equal to O over H. Cosine of alpha is equal to A over H. And then tangent of alpha is equal to O over A. And we're going to use tangent because we already have O and A figured out. If we try to go for sine and cosine, we would have to solve for H first, then we can use it. So tangent is the most straightforward path of least resistance here. So we'll use tangent to solve. And every single time you find the argument, you will always use tangent if you want to do the least amount of work. So I'm going to write out what I just said. Use tan since we know O and A.
And that gives you the alpha.
Yes, that's what I used to get the alpha. So I'm going to set it up over here. Tangent of alpha equals O over A. I always just set up the basic equation with nothing filled in yet. Tangent of alpha is equal to negative 4 over 6. Now, does anyone remember the golden rule of alpha? Yeah, it can't be negative. Alpha is always positive, so if it's negative, make it a positive. It's very simple. Just fix it. Alpha must be positive. I'll explain why in a moment. Just a quick reminder. So if it's not a positive value, make it a positive value. There's nothing fancy I'm doing here. I'm changing a negative to a positive, just because. So reminder why alpha must be positive. Alpha's inside of a triangle, and we cannot have negative angles inside the triangle. Obviously, outside the triangle in the plane, we go negative all the time. We go backwards, it's negative. But alpha inside the triangle, always positive. Always. Theta could be negative, though. So that's why we fix it. If it's not positive, you make it positive. Now we solve. Alpha equals, and then to move the tangent to the other side, that's when we have to use the inverse tangent. Just like we used inverse sine and cosine last unit, same concept. Inverse tangent of 4/6. And then we put it in our calculator and round. Make sure your calculator's in degrees, it should be. Second tangent, 4 over 6. And we're not going crazy this unit with the DMS. We are just going to make it simple, round to the nearest tenth, just like the last unit. 33.7 degrees is the value of alpha. So we now know that alpha is just 33.7 degrees. Lastly, we can use that new number, the alpha value, to find the value of theta. This comes down to the 4 quadrant rules. I've been over them 2 units now. I will show you them again at the end of the notes. But we're in quadrant 4. If you look at theta and alpha together, they create an entire circle, which is 360 degrees. So if I take 360 and subtract the alpha part, I will get what is left, which is the theta. So step 4. Use alpha to find theta. And again, that just depends on which quadrant you're in. So we're in quad 4. In quadrant 4, theta equals 360 minus alpha. That's the rule. That's what I just explained above too. So that's 360 minus 33.7. Theta is 326.3 degrees. So that is the argument of 6 minus 4i. Questions on example 1? Okay. I'll do one more and I can go a lot faster since I won't be writing out the steps. Here. Okay. Now sometimes we won't say argument, sometimes we'll be very transparent and just say find theta. So that's what I'm going to do this time. Find theta, which is the argument, given -5 plus 6i. So first thing we do is we graph. We're going left 5, up 6. So first you just graph your point, draw your line to the origin, and then don't forget to go ahead and draw theta. We start at 0, and then we go up to where the line ends, where the angle line is. This is theta, and this is what we're looking for. Next we draw alpha. Alpha is always drawn from the x-axis to the line. Next step, we draw the triangle. Triangle connects to the x-axis, so we're going to drop it down to make that right angle. Let's go ahead and fill in the side lengths. We know that the vertical is +6. We went up 6, and then we went left 5, so that was -5 on the horizontal. Labeling the HOA, hypotenuse is always in the same place, across from 90. Opposite the alpha is the 6, and then adjacent is -5. So first I find alpha. And like we discussed before, we always use tangents since we know O and A. So we use tangent of alpha is equal to O over A. Tangent of alpha is equal to O over A, that's 6 over -5. And then if it's negative, fix it and make it positive. So actually it's just 6/5. Alpha is equal to inverse tangent of 6/5. And then we plug it into the calculator, rounding to the nearest tenth to get the alpha value. And I'm just going to copy and paste this. Inverse tangent of 6/5, that is 50.2 degrees. So we now know that alpha is just 50.2 degrees. And then we find theta. We are in quadrant 2. So quadrant 2, we know that this is 180 over here. And if we put theta and alpha together, they make that 180. So if I do 180 minus the alpha, I'm going to get the theta that's left over. So the rule is theta equals 180 minus alpha. That's 180 minus 50.2. Theta equals 129.8 degrees. questions on example 2? Before you put away your notes, I am going to write out those quadrant rules again for anyone who wants to see them and wants to write them down. They're the same quadrant rules we've used in previous units. First quadrant, we didn't get that today, but first quadrant is the nicest quadrant because it's where theta and alpha are actually the exact same value. They will always be equal to each other. Second quadrant, we just had that. It's where theta is 180 minus alpha. Third quadrant, we didn't get that today. That's going to be 180 plus whatever additional alpha we have. And the final quadrant, quadrant 4, we had that a moment ago in example 1. That one was 360 minus the value of alpha. So you can either memorize these or you can just be able to look at your problem case by case and figure out the math that you need to do to find the theta. Either one works for me. It's whatever works best for you.